Okay. Welcome back. Anybody want to come up and talk for 5 minutes about what they did on their break? um, okay, so first about the exam. The class average was, I think, pretty reasonable. I think it was about 83%. If you were below somewhere in the 18, I mean, everybody, like everyone has their own ideas of what's acceptable to them. But like to me, if you were below somewhere around 18 or something, you might just want to come bring your test to me and we can talk over some of the things that to me, like that pretty much means for the most part that there were some bigger things that went wrong on your test. So you might want to just come talk to me. Hopefully we can clear some of that stuff up. But like overall, I felt like it was pretty good. And there were a bunch of perfect scores and 23s out of 24 and stuff. So that made me feel like, for the most part, this stuff is making sense. One thing that a lot of people, I only took 1 point off for this, but the last problem, if you remember, so on question 6, you had this object that's under the influence of like a force on the object by this metal arm. And then you had gravity acting down. And the idea was you use the chain rule to calculate the acceleration. Well, let me just go through this one, because actually on this one there were a couple things that that people didn't do right. Carson. Okay, so we know that this is the free body diagram. And so this tells us what all the forces are going to be in Newton's second law. And then we know that the velocity vector as a function of x is x squared 2x. Okay, so the first thing a lot of people did wrong is taking the derivative with respect to x and assuming that that's the acceleration. Okay, the acceleration is dv dt. Okay, that's not the same thing as dv dx. Okay, so you can't do this. So what you have to do is use the chain rule. So the acceleration is dv dt. The chain rule says that's dv dx times dx dt, or dv dx times the x component of the velocity vector. And so in this case, you get 2x, 2, but then you also have to multiply it by x squared. So the acceleration when x is equal to 1 is 2 times 1. So 2. So if you didn't use the chain rule, in this case, actually, you got the you got the right answer numerically. But that's just because the way I set it up, this factor that you have to multiply by, this Vx component, is equal to 1 at the instant that we're evaluating it. Okay, so that was just like a lucky break in this case. So now you can use that with Newton's second law. And also, there were a few people that that went in the right direction but didn't have a free body diagram. I need to see a free body diagram anytime you use Newton's second law or Rn2L. Okay. So I took a point off for no free body diagram or an incorrect free body diagram. So we have the left side of Newton's second law comes straight from the free body diagram. So you have F, OA, X and Y components, plus 0, negative 49.05, negative 49.05. Somebody multiplied 5 times 9.81 and got 19.62. Man, that just cracked me up. That was so good. I just showed that to everybody. Just kidding. I didn't take any points off for that. But it's not. It's 49.05. Just keep working on that arithmetic. It'll come. And then the mass is 5. The acceleration vector is 2, 2. And so you come up with this force vector FOA is equal to positive 10 newtons, positive 59.05 newtons. Okay, and then once you get there, a bunch of people, I only took 1 point off for this, but I didn't ask for the force on the object by the arm. I asked for the force on the arm by the object. So now you have to just use Newton's third law and say F on the arm by the object is equal to the negative of the force on the object by the arm. So the final answer should be negative 10 newtons, negative 59.05 newtons. And that was the trickiest of the 3 problems for people. Also, a lot of people miss points on those quiz questions. It made me think, you know, I didn't say this explicitly at the beginning, but to me, those should just be sort of free points, you know. I'm going to start giving quizzes again, starting with this lecture. Maybe I would recommend so take the quiz and just go back when you take the next quiz or whatever, go back and look at those answers, refamiliarize yourself. It can be sort of hard to stick all that information in your head right before the exam. And it doesn't last as long either, so that's why I don't want you to do it that way, because I want you to remember the information beyond just like when the test is. Just go back to those quiz questions and remind yourself of the answers as you go. And then you won't have to worry about trying to cram that in at the last minute while you're also trying to remember how to do these calculation methods. So, you know, a person could have gotten, could have done all the calculations perfectly and still gotten like sort of a middle C type percentage on the exam by missing all the quiz questions. So that can add up, you know. Any questions about the test? Okay. If you have any questions, if you think I misgraded something or took off more points than I should have for something, I mean, basically the the formula is if I think something is insignificant, like something I know you know how to do, and it was just under the pressure of the test, like 5 times 9.81 is 19, I don't take off any points. If you make more than one mistake like that, or if you make what I consider to be a fairly small mistake, I take off a point. If I consider it a big mistake, I take off 2 points. And the biggest type of mistakes, like a real fundamental misunderstanding of something, I'll take off 3 points. And that's just sort of how my scoring works with these. Okay. So who remembers what class this is after break? No. That's close, though. Dynamics. Every class is a little bit arithmetic. But did I tell you guys that a friend of mine has a friend who worked in a community college in Michigan? He's like a math instructor at this community college.
What community college? I just moved to Michigan.
Oh, you did? I don't remember. Somewhere up north. And someone came into his office and was like, I'm really good with my pluses, but I'm having some trouble with my takeaways. He's just like, this is what I got a PhD in math for? Okay, so this is dynamics. Nothing against Michigan, though. Oh, yeah. So it's dynamics. And we're working on rigid body kinetics. And we're about to use rigid body kinetics to solve linkages. Collections are rigid bodies connected by joints. So because we're gonna be using the methods for solving rigid bodies, I'm gonna just refresh our memories about the steps for solving a rigid body, and then I'm gonna go into how to use this to solve a linkage. Okay, so as a review, steps for solving a rigid body. We're talking about kinetics. So without looking back at your notes, anybody remember what the first thing we have to do? We see this rigid body, it has forces on it. We're trying to calculate something about the accelerations. What? Well, there's something you have to do. That's right. So the first thing you need to do, and really, I mean, this is just the order that I gave it in. Drawing a free body diagram is a perfectly good first step, but if you're going to follow the order that I gave, you have to figure out, does it rotate about a fixed point, or are there no points on the body that are fixed in your coordinate system? If there is a fixed point, then your about point is that fixed point. If there's no fixed point, your about point is the center of mass. The second step, once you've chosen that, why not calculate the moment of inertia? These first three steps you could sort of do in any order. No, you could do that's not true. Do it in this order. Why not? So the next thing you have to do is calculate the moment of inertia about whichever about point is you chose. And notice you have to use the parallel axis theorem if the about point is what? That's right. So if A is a fixed point, yeah, that's the best way to say it, I suppose. If the about point is not the center of mass, you have to use the parallel axis theorem. So in most cases, if there's a fixed point, you're going to have to use the parallel axis theorem. Third free body diagram. Fourth, professional aquanauts, row 4, money. So once you have the free body diagram, you can fill out this table. Next, if your about point is a fixed point, you can skip this step. Otherwise, you're going to have to use Newton's second law. So F is equal to ma, and a is the acceleration of the center of mass. And the left side comes from the table, the fourth column of the table. Six, rotational Newton's second law. So that says add up all the external moments about your about point. That's equal to the moment of inertia times the angular acceleration. And these moments, the left side of this equation, come from the moment column. So that's what makes that table nice. And so now you have all your equations of motion. The next step, you're often going to have to do this. So I put it down as a step, but there's nothing saying that this is required. Maybe you're in the problem, you're asked for something that you can get directly from these. But if you want the acceleration of some point, okay, and by the acceleration of some point, that means we want the acceleration of that point relative to the origin. Then we're going to use the relative motion equation. And we're going to use the rotational kinematic equation for acceleration. So can you think about this for a second? Can you think of a case? So think of the two cases that we're dealing with. Your about point is the center of mass, and the about point is a fixed point in the coordinate system. In which of those cases are we going to need to use this relative motion equation? Only one of them. Yeah. So fixed point or center of mass, okay? If we're trying to calculate the acceleration of some point on the rigid body, okay, away from that about point, no matter what, we're going to have to use this, this rotational kinematic equation. But in only one of those two cases are we going to have to use this relative motion equation. Do you have a feeling for which one of those you won't need that for, which one you will need it for? For 50% chance. It's so you're going to need this for the when the about point is the center of mass, okay? Because if the about point is the fixed point, okay, what's the acceleration of A relative to O? Is zero. There, that fixed point is, you know what I mean? If, okay, so say you have something like this, and this fixed point is A, okay? So this point isn't going anywhere, no matter where the coordinate system is, right? So what's the acceleration in this coordinate system of A? It's zero, right? And so this equation reduces down to just saying, forget about all that. And you can just calculate the acceleration of that point P as this, okay? That'll make more sense as we start to do a bunch of examples. More than 0 cents, it looks like. More than the 0 cents it makes right now.
So, if something is not, if a body's not fixed
Mm-hmm.
at a given point, it's always any force because it's rotatable, always supposed to rotate.
Okay, so yes, that's right. That's right. Any force that acts, so say an object's just free to spin in space or on ice or whatever, any force acting through the center of mass will not make it rotate. Any force not through the center of mass will make it rotate. Well, think of a rotation. Those rotational quantities don't have an about point, you know? Something just either rotates or it doesn't. You know what I mean? Like there's no point associated with calculating the angular acceleration or the angular velocity. Those are like absolute quantities. But if you apply a force through the center of mass, it won't create any angular acceleration on the body. So if this board is just sitting on the ice and you apply a force through the center of mass, it'll just translate without any rotation. If you apply it off from the center, it'll spin. So we do those calculations about the center of mass, but really, like physically, a rotation is just a rotation. It's just a changing of orientation. Okay. Okay, so now we're going on to linkages. And you know, what's a linkage? So this pair of grippers is a linkage. It's a collection of rigid bodies connected by joints. Okay, and say that we knew external forces here at the head and external forces here on the handles. Could we calculate what the accelerations were on this thing? Okay. In 2 dimensions, this is kind of an aside, but in 2D, these joints will almost always be pin joints. And I'll give you a list of the load types provided by a bunch of different joints. But before I go into that, let me just say, so a pin joint, what kind of load does a pin joint apply to a rigid body it's connected to? Okay, so if you have a, this is from statics. If you have the free body diagram of this object, how do you treat this external load provided by the pin? Well, you're right. It would be 0 if there's no, if there aren't any other loads. But say that there are other forces making. So what's this pin joint doing to hold this thing on here? You know? Yeah, and actually, so it's holding it in place. We treat it like we don't know the direction because that pin joint can provide any force. The way to think about the loads that are provided by any joint is to think what motions are not allowed by that joint. Okay? Whatever motions aren't allowed, the joint has to provide a load that restricts that motion. Okay, so does this pin joint let this body move in the x direction? No, so there has to be a force with an x component. Does it let it translate up and down? No. So it's an unknown full force vector, force on the object by the pin. So now what about a couple? Does it let this object rotate about that pin? Yes. So it doesn't provide any couple. So this is the type of load that it applies. Okay. So pin joint, there's always just going to be a force vector applied. Well, we just treat it like there's an x component and a y component, and the positives and negatives will come out on their own. Okay. So yeah, you don't have to think too much about. It turns out you don't have to think at all about what directions they're actually going to be. There's going to be an x and a y component, and we'll just solve for them. What do you think about, what about a pin joint in 3D, by the way, using that same type of thinking? Let's see if I can draw that. Okay, so the pin goes through this way, and say that this is your x-axis, y-axis, and z-axis. So this is in 2D, which is what we're pretty much always going to do. But in 3D, what is this pin joint? Yeah, most of the time, like the way I have it drawn, it doesn't let it move in any linear direction. Although depending on the type of pin, it could let it slide along the axis. And what about couples? We know that it's free to rotate about the z-axis, but the other two it applies. So there's a couple in the x direction and a couple in the y direction. And it just lets it rotate about one axis. That's all it lets it do. Okay. So with linkages, the idea is this. We're going to solve each rigid body. And then we're going to need constraint equations. And that says that adjacent bodies agree about the acceleration vector at the joint that they share. Okay, so let's go through an example. And after I do this example, I'll go into all the definitions of the different joints, give you the ways to treat the different joints, and I'll give you a complete method, set of steps for solving these linkage problems. And then you're just going to have to do a bunch of these, and once you do a bunch of them, it just sort of becomes automatic, the same way this kind of stuff did in statics. Okay. Okay, so here's an example. So say you have these two slender rods hanging down from a pin joint. Say the length of each one is 1 meter. And each one has a mass of 10 kilograms. We'll call this one member 1 and this one member 2. And let's say at this instant, the bodies have no angular velocity, so they're hanging there at rest. And say that a couple is applied of 5,000 Newton meters to body 1 at this joint. Okay? That could be a motor applying that, a screwdriver or whatever. Who remembers what a couple is? Who remembers hearing the word couple? Okay. Yeah, exactly. So the important thing to remember is a couple you can treat as just a pure moment. So as a pure moment, it's the same no matter what your about point is. And that's a key thing. So when I say that this couple is applied at the joint, that's extra information. That doesn't matter at all. Okay. That would matter if you're doing the deformable body mechanics on this and trying to calculate stresses, but not for us. So it's the same no matter what about point you choose. And it's called a couple because, like you said, it's created by pairs of equal and opposite forces acting at a distance. Okay, so like when in football, a 300-pound guy applies a 10,000 Newton force at someone's ankles, and another 300-pound guy applies a 10,000 Newton force at the shoulders. Those are equal and opposite forces acting at a distance. That's a couple, and it makes the guy rotate very quickly onto his face, So the word couple is because it's created by equal and opposite pairs of forces, couples of forces. Okay. But mathematically, we just treat it like it's a moment, and no matter what your about point is, when we deal with this body, we're just going to add this 5,000 Newton force on there. Okay, so it just goes sort of alone in the it goes alone in that moment column of the table. Okay. Okay, so what we want to do is solve each of these two bodies, and then we want to add up variables, add up equations, see how many constraint equations we need, and go from there. Okay. So first, let's do body one. Okay, so step one. Does body one have, and let's choose a coordinate system. Let's put it there. Does body one have a point? Like, is there a point on body one that's fixed in the coordinate system? Yes, it's at that joint. And it's at the origin. So the second step, we're going to calculate the moment of inertia. So first we have to do the moment of inertia about the center of mass. That's 1/12 times the mass times the length squared. And I don't have that. Can someone calculate that? 0.8, yeah, 0.83 is repeating. What? I think that's what, yeah, 5/6 I think is that. Okay. And so then the moment of inertia about that fixed point is 0.833. We have to use the parallel axis theorem here because it's not about the center of mass, plus the mass times the distance squared. What's the distance? What? 0.5, yep. And so this, I know, is equal to 3.33. But that's what I have anyways. Okay, so step 3, free body diagram. This is a pin joint. So the force here is, I don't know, let's call that the reaction force at A. Then there's a weight force, 98.1 newtons acting down. There's a couple, and we'll put that on here like this, and we know the magnitude of that is 5,000. And then there's one more force. Yeah, and actually, okay, so we don't know that it's pulling down. I mean, think about what's happening with that. If it was just hanging there with no forces, then yeah, it would just be pulling down. But this couple's doing this, it's going to start to accelerate, like this is going to start to rotate counterclockwise. We don't have intuition about that, okay? So for now, we're just going to say that's a pin joint, and that's all we know. So we're going to treat that as the force applied to body 1 by body 2. Okay, and it's a force vector because it's a pin joint. So the next step is the table. Professional, aquanauts, row, for, money, or some variation. Whichever one you think is the most hilarious on that day. So the weight force, what are the coordinates of where that weight force is acting? Yep, 0, negative 0.5. The about point, what are the coordinates of the about point? Yep. Subtract those, and your row vector is 0, negative 0.5. What's the force vector? Yep. What's the cross product? This minus this? Zero minus 0, 0. And that makes sense, right? Like we're calculating the moment about this point. What's the weight of it? Like the weight isn't going to make that rotate, you know. Okay, the next force, how about this RA? So that's acting at the origin. That's also the about point. So the row vector is zeros. We don't know what this force is. Call it RAX and RAY. But it doesn't matter what it is. It's still 0 minus 0 is 0. Now this couple. This couple, I don't know. This problem says where it's applied, but it doesn't ever come into anything. You can leave everything blank and just put positive 5,000 for the moment. It doesn't produce any force. And why doesn't it produce any force? I mean, if it's made up of a pair of forces, why don't those appear here? They're equal and opposite, exactly. So they just cancel each other out. Okay, and then so we have 1, 2, 3. The last load that we have to deal with is this F12. That acts at 0, -1. The about point is zeros. So the row vector is 0, -1. The force is F12x, F12y. And so the moment is F12x. Do we need step 5 for this body? It has a fixed point, so we don't need it. We only need it when we're dealing with the center of mass. So no step 5. So step 6, rotational Newton's second law. Add these up. 5,000 plus F12x is equal to 3.333 times the angular acceleration. Okay, so let's take inventory of this. Call that equation 1, okay? And let's think about how many variables, what the variables are that we have. In our equation of motion, so we've defined a few variables, right? But in our equations of motion, the only ones that we're left with are F12x and alpha, okay? So right now we have one equation, 2 variables, so there's nothing we can solve, okay? But these are going to be useful, so we'll just move on to the next body and see where we stand, okay? Any questions yet at this point? So now we're going on to body 2. So step 1, is there a fixed point for this body? Right. So that's an easy mistake to make. There's a pin joint here, and it's easy to think like, yeah, it's rotating about that pin joint, but that pin joint can move, right? So in this case, there's no fixed joint, and we have to do everything about the center of mass. So the about point is the center of mass. So for this second one, the moment of inertia about the center of mass is equal to, we calculated that before, 0.833. That's 1/12 times 10 times 1 squared, so 0.833. And now the free body diagram. What loads are acting on this second body? This can start to get a little like, if you're just trying to sort of write stuff down as you see it in complicated problems, in these linkage problems, it can get a little too complicated. You start missing stuff. So just think of it this way. There's always going to be a force applied by gravity, and then you're just going around the outside of the body looking for contact and external loads. on that body, on the outside of the body. So, so first there's going to be a weight force, 98.1. And now just think about going around the outside of the body looking for places where there's contact. Okay? The only force is happening at this pin, right? This couple is applied to the other body. It's not touching this one, so that doesn't appear. Okay? So up here we have a force on body 2 by body 1. Okay? You can recognize it now or recognize it later that we can use Newton's third law here. Okay? I'm gonna leave it like this for now and reduce the variables using Newton's third law after we get all the equations written. Okay? So step 4, professional aquanauts, row 4, money. So first, let's deal with that gravity force. If we use that same coordinate system, what's the location of the weight force? Yep, 0, negative 1.5. What are the coordinates of the about point? In this case, yeah, right. So 0, negative 1.5. So the row vector is 0. The force vector is 0, negative 98.1. And so the moment is 0. And I sort of purposely alternate between writing when we're doing 2D problems, writing my moments as, sometimes I write them as 3D vectors, sometimes I write them as scalar values. What does this scalar value correspond to as a 3D vector? 0, 0 value, yeah, right. Okay, and then one other force, this F21. What's the location of that force? Mm-hmm. The about point stays the same, so 0, negative 1.5. So we have 0, positive 0.5 for rho. The force vector is F21x, F21y. So the moment is negative 0.5 F21x. For this one, do we need step 5? Newton's second law? Yeah. So we have 0, negative 98.1. Plus F21x, F21y is equal to the mass times the acceleration of the center of mass, x and y. We don't know anything about the direction of this acceleration, so this just has to be a vector. And then step 6. So this is Newton's second law, rotational Newton's second law. says 0 minus 0.5 f21x is equal to 0.833 angular acceleration. Oh, up here. Back in the first body, I just forgot to label this. So these bodies can rotate independently, right? So I just have to make this angular acceleration of body 1. And then we'll have a separate angular acceleration of body 2. Okay, so now before we update our equations, so now we've solved both bodies, right? Can we reduce the number of variables using Newton's third law? Yeah, well, the question is, are any of these just flipped versions of things that we already have in our list of variables? And yeah, F21 is just equal to F12. So I can rewrite the equations in step 5 and 6 as negative F12x is equal to 10a center of mass x, and negative 98.1 minus F12y is equal to 10 acceleration of the center of mass y, and then positive 0.5 F12x is equal to 0.833 alpha 2. So these are equations. We had one equation already, right? So this is equation 2, equation 3, and equation 4. And now let's take inventory of our variables. Where are we with the variables? Well, from before, we had F12x and alpha 1. Now we also have F12y introduced in this set of equations. And we also have the acceleration of the center of mass, full vector, for body 2. And then we also have the angular acceleration of body 2. Okay, so can we solve this system? No, we have 6 variables, 4 equations. So we need 2 constraint equations. Okay, that's one vector constraint equation. So we need one 2-dimensional vector constraint equation. And that will come from calculating the acceleration of the pin according to body 1. Calculating the acceleration of the pin according to body 2, and requiring that they accelerate together. Okay, that's what that joint does, is make them move together. Okay, so let's first do it according to body 1. How do you calculate the acceleration of, where is this problem? How do you calculate the acceleration of this point according to body 1? We can just use that rotational kinematic equation. Okay, you can think of it as the acceleration of P is equal to the angular acceleration of body 1 crossed with this r vector for body 1 plus omega of body 1 crossed with omega of body 1 cross r1. What's the r1 vector? Negative point, yeah, right. 0, -1, right. So r1 is 0, -1. So the acceleration of that pin is equal to 0, 0, alpha 1 crossed with 0, -1, 0 plus, who wants to calculate all this stuff? I will, 0, yeah. Because we don't have any angular velocity. Okay. And that tells us that, let's see, take the cross product here and you get alpha 1, 0, 0, right? In 2D, that's just alpha 1, 0. Now we have to calculate the acceleration of P according to body 2. And this one doesn't have a fixed point, so this is the one where we're going to have to use the relative motion equation and that rotational equation. Okay, so the acceleration of P relative to the origin is equal to the acceleration of P relative to A plus the acceleration of A relative to the origin, and the acceleration of P, and what's the A? The A here is going to be the center of mass. Okay, so the acceleration of P relative to the center of mass is equal to alpha 2 crossed with R2 plus omega 2 crossed omega 2 cross R2. So we get 0, 0, alpha 2 crossed with, what's R2? This time, so that R is going from the center of mass to the joint. We're doing the rotation about the center of mass, assuming that center of mass is fixed. Okay, that's what this equation says. That's a relative motion according to that center of mass. Positive 0.5, yeah, in the y direction. So 0, positive 0.5, 0. This stuff's all zeros. So we get negative 0.5 alpha 2, 0. So I think you're noticing this, or you noticed it 20 minutes ago. This stuff has a lot of steps, you know. There's a lot of steps. Like, what you have to keep grounding yourself to is just sort of the big picture, you know. Like, we're solving each body, and after we solve each body, we're constraining those bodies at the joints, okay? That's what we're doing. So, I don't know. And you'll get more comfortable with it as you get practice with it. But I know it's easy to get lost in this stuff. But now we've calculated the acceleration of P, assuming the center of mass is fixed. Now we're going to use this relative motion equation. And so the acceleration of P relative to the origin is what we just calculated, 0.5 alpha 2, 0, plus the acceleration of the center of mass, x and y, and finally our constraint says this is equal to this. So the constraint equation says alpha 1, 0 is equal to negative 0.5 alpha 2, 0 plus acceleration of the center of mass, x and y. We already have 4 equations, so these are equations 5 and 6. We didn't add any new variables. These are all variables that are already in our list. They already appeared here. So now we're done. We have a 6x6 system that we can solve. Yeah, it's a vector. So alpha 1 is equal to negative 0.5 alpha 2 plus ACOMX. That's equation 5. And so plug this into your solver and you get, what did I call that reaction force? RA. RA is equal to 64, 29.12, 196.2. F12 is equal to negative 2142.61, negative 98.1. And I didn't write it down here, but you also, would get the, in order to solve these, you have to solve for those other 4 variables too. So there's 2 variables. Here's another one. And here's another one. Okay. So there's like a million places to make calculation mistakes. You probably won't lose any points on a test for making a calculation mistake. You just need to get to the point where you need to show me that you understand how the steps fit together. Oh yeah, yeah, right. I mean, this is like the simplest linkage possible, and it was 6 by 6. So we won't do any super complicated ones. And so what would you do in practice? I mean, you would write a MATLAB program that does this, I mean, if you were solving a linkage of 30 bodies, which probably, that's not even a very complicated robotics problem, I mean, imagine it goes up. Basically, every body is all the loads plus new variable, like all the variable loads get added at each body, plus the acceleration of the center of mass and that body's angular acceleration get added. So every body has a minimum of 3 new variables, So yeah, it gets pretty messy. So we're only gonna do the simplest problems, ones with 2 and sometimes 3 members. On exams, it'll only be 2 members. Like otherwise it would just take too long. Any questions about that? My advice would be make sense out of the big picture first and then worry about the details. Like don't sweat the details until you sort of follow the flow of what's going on. But next class, I'm going to give a general method for solving linkages. I'm going to go back, and I know you had this in statics, but I'm going to talk about how to treat the individual types of joints. Usually you'll just have pins anyways. And then we'll do an example problem where you can work together on it and try to fight through this. Okay, that's it.